Hello everyone, welcome back to Simscope. Today we are building and analyzing a single phase inverter using the unipolar PWM in Simulink. The goal is very simple. We will convert the DC power into AC power, and we are going to learn the unipolar PWM modulation in the H-bridge inverter. Firstly, the single phase inverter. So what is inverter? Inverter is a electronic device that will convert the DC power into AC, and where it is used, usually our home solar home lighting systems, like it uses the solar panel produces a DC power, battery stores the DC power, but the appliances that we are using in our homes and offices are runs on AC power. So inverter is required to convert that DC power into AC. So that's where we the inverter comes in. And in this simulation, the inverter I'm going to show is switched, not simply switched on the square waves. We will be using the PWM. What is PWM? PWM means the switches turns on and off at a very high frequency. By turning them on and off, we the pulse width are varied according to the sine reference. By doing this, we can control the AC fundamental components like voltage, and we can get the voltage, output voltage at the magnitude that we want. And how do we do that? We do that by changing the modulation index. Okay, moving on to the model architecture, we have DC voltage source of 100 volt, and this is the H-bridge inverter. I have load, RL load. My resistance is 1, and inductance is e to the power minus 3. I will give my, anyways, I'll keep my load same for now. Then I have measurement blocks to measure the current and voltage generated by the inverter. And scope 2 is showing me the raw unfiltered and rough AC waveform. At the bottom, we are making the pure sine wave by using the low pass filters, and scope 3 is going to show the smooth smooth sine wave waveform. Okay, and this subsystem is a gate pulse circuit. This gate pulse circuit has sine wave, repeating sequence, operational comparators, and they are giving the PWM signals to this H-bridge transistors. In case of the H-bridge inverter, we have 4 switches. It can be MOSFET or IGBT. T1 and B1 makes one leg, T2 and B2 makes another leg, and in my model, I'm going to use a discrete. The power give is set to the discrete mode with a simple with the sample time of 1 e to the power minus 6 seconds, because the PWM switching needs a very small simulation steps. And why it is important? because the PWM pulse are very fast and the coarse sample time can either miss the switching events or produce incorrect results. Okay, I'll explain how the H bridge works. The full bridge inverter reverses the voltage across the load by turning a different switch pairs on. And in a unipolar PWM, each leg is controlled separately. So this allows the output to take three different voltage levels: positive, zero, and negative voltage. That means we can see at the output we can see positive voltage, zero, and negative voltage, making a sine wave. Now if we turn on the switch T1 and B1, then we are going to see the positive voltage at the output. And if we turn the T1 and T2, if we T1 and T2 is on, then we're going to see the voltage 0. If the B1 and B2 is turned on, then it will be again 0. And to see the negative voltage, your B1 and T2 should be turned on, then your load will see the negative voltage. Now moving to the pulse width modulation, we have a sine wave, and this sine wave reference is compared with the triangular carrier. For the leg A, the sine wave is used directly, and for the leg B, sine wave is inverted. The bottom switch B1 and B2 are produced. Bottom switches are produced using NOT gates, so that each bottom switches is complementary to the corresponding to the top switches, and this will prevent the top and bottom devices in the same leg from being on at the same time. We do not want to turn it on at the same time. Okay. Okay, this one. Now, for the carrier, we can say that if the V reference is greater than or equals to the V carrier, then T1 and B1, T1 will be turned on and B1 will be turned off. To see the negative voltage, negative V reference, here the negative V reference should be greater than or equals to carrier V carrier, then the T2 will turn on and B2 will turn off. Now that is how we turn on the switches, and these pulses are given to the gate of the IGBTs, controlling this uh, IGBTs or MOSFETs. Now, one important mathematical thing we have to do is the parameters. Here I'm giving the input of 100 volt VDC, and I have my modulation index MA as 0.5. Where is that? Yeah. Okay. Now some important parameters here. My frequency is 50. The resistance at the load is 10 ohm, and I want to see in the two different loads. The load one will be a purely resistive load of 10 ohm, or the inductive load will be 1 ohm with, I'll put some these values. Then for the modulation index, how do we calculate? Modulation index, V reference divided by peak V reference divided by peak area. So the modulation index decides how much the fundamental AC voltage is produced, and in the linear SPWM region, the modulation index should always be less than or equal to 1. If the modulation index increased above 1, then inverter will enter into the overmodulation phase and the output will become more distorted. So as per our project here, we have the output voltage, peak voltage is equals to modulation index times VDC. Then we are going to get the V output approximately 50 volt. Then the RMS voltage will be 35, approximate 35.36 volt. The resistive load calculation, my current will be approximately, load current will be 5 amps. The power should be 125. For RL load, I've also calculated here. Okay, then load variation results from the calculations are like, if I give my load, if my load is 2 ohms, then voltage, current, and output will be something like that as per the. At the output filter calculation, we have, what do we have in the output? Two first order simulation. Now we have one transfer function and another transfer function, and we are using two first order transfer function blocks at the output of the voltage and current measurement. For current measurement, same, we're using two first order transfer blocks, and it is a first order low pass filter. And what does it do? It will filter the raw waveform into a clear sine wave. So the cutoff frequency should be 50. The low pass filter is in this form, this equation. Then by using this, we are we are reducing the ripple. Okay, I will run the simulation once and show you the okay, let's see the raw waveform. Now you can see that the voltage, positive voltage I'm getting is 100 and negative 100. So amplitude is 100 volt. The blue waveform is a current waveform, so my current is approximately 21 point something, and I am giving an input of DC voltage of 100 volt. I'm getting output positive 100 going to negative, positive, negative, positive. So it makes a sinusoidal wave, and we have converted 100 volt DC power into the AC power. This is the raw waveform. It switches very rapidly in the very short period of time in 0.0. So this is the inverter, but we can see that this waveform is not smooth enough and does not create a smooth sine wave at the switching mode. So instead, it creates a pulse whose average value follows the sine reference, and the high frequency components are later reduced by filtering and the low inductance are used. So let's see now the filtered voltage waveforms. Scope 3 is showing me this. I have the first waveform is the voltage waveform. When we filter the voltage, you can now see that my magnitude of the voltage has reduced from 100 to approximately 50. The filtered voltage is close to sinusoidal. It is showing a good sinusoidal wave. It is more smooth, and the observed peak value is approximately 48 to 50 volt. So which we agrees that theoretically when we calculate, it was giving us a 50 volt peak. Now at the bottom we have a current waveform. It depends strongly on the load. The current waveforms depends on the load. With the resistor, the current is in phase with the voltage. If I want to show this in, okay, you can now see that it is in phase with the voltage. And in case of the RL load, current will always lag. This is a RL load, so current lags the voltage and it becomes smoother. This happens because the inductor resists the rapid current change and filter the switching ripples. Okay, now what we can see and say about this is, mm, in the engineering ideas, we can say that inverter outputs depends on the modulation index. If we change the modulation index, then mm, you can get the voltage magnitude of different voltage magnitudes. So by changing the modulation index, we can control the output voltage. But the inverter output depends on the modulation index, then switching frequency, it depends on the load impedance, and finally the filter that we use. By increasing the modulation index, we can increasing the modulation increases the AC output voltage. Increasing the switching frequency usually improves the waveform quality, but it also increases the switching losses. Then lower resistance will increase the current and thermal stresses. Higher inductance will smooth the current but increase the phase lag. Okay, thank you for watching.